13.8 billion years ago, the universe began as a single, infinitely hot, dense point. That point erupts outward, initiating an ongoing, violent expansion. George Lemaitre formalized this model in 1931. His Big Bang theory established the consensus for an expanding universe. For decades, it competed against the steady-state theory, championed by astronomer Fred Hoyle. Hoyle's model agreed the universe was expanding, but argued it maintained a constant average density as new matter continuously formed. Regardless of whether the origin was a sudden explosion or a steady state, the resulting universe is a kinematic arena. It is defined by outward expansion and localized pockets of intense, self-organizing rotational energy. Scale down from the cosmic web to a localized cloud of dust and gas, roughly 4.8 billion years ago. The nebular hypothesis, initially proposed by Immanuel Kant and later revised by Pierre-Simon Laplace, details how this static nebula began to spin. As the rotational velocity increased, it generated massive centripetal forces, forces that pull mass inward toward a curved path center. This animated diagram of the spinning nebula's cross-section shows a strict density sorting mechanism. Gravity and centripetal forces drag the lowest density elements, specifically hydrogen and helium, directly to the center, pushing heavier debris outward into a flat disk. That central mass pooled into a composition of roughly 70% hydrogen and 30% helium. When it reached the required critical density and temperature, it ignited the sun. The ignition of the sun left behind the spinning disk of heavier debris. These were the raw architectural materials that would eventually clump together and cool to form the planets. Zooming out to view the entire newly formed solar system reveals a strict physical and compositional boundary line, the asteroid belt. This comparative data matrix highlights the inner or terrestrial planets, Mercury, Venus, Earth, and Mars. They sit inside the belt. They are small, rocky, and feature extremely high physical densities. Earth holds the absolute highest density at 5.5 grams per cubic centimeter. Beyond the asteroid belt sit the Jovian, or outer planets, Jupiter, Saturn, Uranus, and Neptune. They are incredibly massive in physical size, but because they are composed entirely of gas, their relative densities plummet. Saturn illustrates the extreme physical reality of this low density. At just 0.69 grams per cubic centimeter, Saturn's density is so low that it would theoretically float in a massive ocean of water. The solar system is a highly organized thermodynamic engine, sorted cleanly by mass and density across a single rotating plane. A planet's orbital speed, its revolution around the sun, is dictated strictly by its proximity to the star. Mercury is the closest, and it completes a full orbit in a blistering 88 days. Rotation is a planet's spin on its own axis. The massive gas giant Jupiter possesses the fastest rotation in the system, completing a full spin in just 9 hours and 55 minutes. Most planets rotate counterclockwise from west to east. Venus and Uranus are the only two planets in the system that rotate in retrograde, spinning clockwise from east to west. Uranus features an extreme geometric anomaly. It has a 98-degree axial tilt, causing it to roll along its orbital path rather than spinning upright like a traditional top. These extreme kinematic quirks, like hyperfast spins, complete backward rotations, and severe tilts, are the surviving mathematical scars left by violent, massive asteroid impacts during the solar system's formation. Zooming in from the orbital plane directly to Earth, the planet initially presents as a pristine, mathematically perfect sphere. This 3D wireframe illustrates how rotational velocity deforms Earth. The spin generates centrifugal force, an outward push on rotating mass. This expands the equator and flattens the poles, creating an oblate spheroid. Consequently, Earth's equatorial radius is physically larger than its polar measurements. This physically stretched, slightly uneven shape is called a geoid. It serves as the irregular canvas upon which humanity projects a mathematical grid to navigate space and time. The horizontal mapping grid consists of latitudes. There are 181 total lines running east to west across the globe. They maintain a fixed, uniform distance from one another, exactly 111 kilometers apart. Because of the geoid shape, there is a geometric limitation. A great circle perfectly bisects a sphere. The equator, at 0 degrees, is the absolute only latitude line wide enough to qualify as a great circle. The vertical grid consists of longitudes, or meridians. There are 360 of these lines. Because they converge at the poles, the distance between them is variable. They shrink from 11.3 kilometers apart at the equator, down to 0 at the poles. To map a sphere, you need an arbitrary starting line. The man-made anchor point for this longitudinal grid is the prime meridian, located at 0 degrees at the Royal Observatory in Greenwich, London. This is the physical demarcation line in Greenwich, where the global mathematical baseline is anchored securely to the ground. This polar view of Earth divided into 24 sectors illustrates the connection between spatial geometry and time. Earth completes a full 360-degree rotation every 24 hours. This means it rotates exactly 15 degrees every hour, breaking down to 1 degree every 4 minutes. This rotation establishes the rigid rule of global timekeeping. Moving east from the prime meridian adds time, while moving west subtracts it. Apply this to a real-world calculation. India's standard meridian is located at 82.5 degrees east. Dividing 82.5 by 15 degrees results in exactly 5.5. This mathematical reality dictates why Indian Standard Time is strictly 5.5 hours ahead of Greenwich Mean Time. The hours on a clock, the borders of a time zone, and the dates on a calendar are direct mathematical translations of an oblate spheroid spinning through the solar system.